We are looking at a paper today that potentially solves, I think, the single biggest frustration with AI image generation.
Oh, yeah. Which one?
It's titled Think, Then Generate, Reasoning-Aware Text-to-Image Diffusion with LLM Encoders.
Ah, okay. The one from Shanghai Jiaotong University, Kuishu, and Tsinghua.
That's the one.
This is a heavy hitter. We're talking about moving past the era where your AI model is just a fancy parrot that matches keywords to pixels.
Right, because right now, even the best models, Flux, Stable Diffusion 3, they're essentially just text pixel mappers.
Exactly. You give them a prompt, they map it to a visual,
Yep.
but they don't actually understand what they're drawing.
A perfect example is if you ask for ice cream exposed to the sun.
Right. A standard model hears ice cream and sun and just gives you a bright, sunny picture of a perfect ice cream cone.
It completely misses the causal link, the physics, that the ice cream should be a puddle.
Yeah, a mess.
And that is the core problem this paper tackles. They're introducing this new paradigm called Think, Then Generate.
The name says it all, really.
It does. They force the large language model behind the scenes to stop being like a frozen statue and actually perform chain of thought reasoning.
Before it tells the image generator what to do.
Exactly. And the results are genuinely startling. They got a 0.79 score on the WISE benchmark, which tests world knowledge.
That absolutely crushes the open source heavyweights. Flux, ST3.5, it beats them by, what, 30%?
Roughly 30%. But the real headline here, that score puts them right on par with GPT-4o.
Which is closed source and, state of the art.
So let's back up a bit and unpack why our current models are so bad at this. We tend to think of them as smart because they render such beautiful lighting and textures.
But they're not. This paper argues they are structurally handicapped.
So it's an architecture problem.
It is. It comes down to the architecture. Most modern diffusion models, they use a massive LLM, like a T5 or a CLIP, as their text encoder.
But in almost every training pipeline, that LLM is frozen.
Completely frozen. It's strictly a feature extractor.
So it just takes your text, turns it into a mathematical embedding, and then passes it on.
Yep. It's not allowed to think or process the logic. It's just a translation layer.
It's a correlation engine, not a reasoning engine.
Exactly. It operates on a bag of words principle, implicitly. The paper highlights this with a chemistry example that I just loved.
Oh, which one?
The prompt was, a glass of hydrochloric acid and phenolphthalein mixed liquid.
Okay, so if you remember your high school chemistry, phenolphthalein is a pH indicator. In acid, it's colorless.
It's colorless. But if you feed that prompt into a standard model like Flux...
What happens? It probably just sees the word phenolphthalein and associates it with pink.
Exactly. It just draws a generic pink liquid, or sometimes a beaker with separated colors. It's just pattern matching keywords.
It has no concept of simulating the chemical reaction.
It's guessing based on aesthetics, not logic.
There was another one about a math teacher explaining 2x minus 4 equals 10.
Oh, the classic AI text failure.
You get this photorealistic teacher, beautiful chalkboard.
And the writing on the board is absolute alien gibberish, or just, random numbers.
Because the model doesn't understand the relationship between the numbers.
It just knows that math teacher usually correlates with white symbols on a black background.
Right.
The Think Then Generate paradigm just flips this completely. It says, before we generate a single pixel, we need to retrieve world knowledge.
We need to solve the equation.
We need to solve it. Add 4 to both sides, divide by 2, x equals 7, then we draw.
So how did they actually build this? It's a 2-stage post-training pipeline, right? Phase 1 is supervised fine-tuning, or SFT.
Yeah, basically teaching the model to talk to itself.
Which means they needed a new data set.
Right. They had to create one to teach this behavior. They used Gemini 2.5 to curate about 7,000 samples.
And what was in it?
They took these really hard prompts, ones requiring logic or physics, and had Gemini generate a chain of thought reasoning trace followed by a refined prompt.
So the pipeline changes. Instead of prompt to image, it becomes prompt, internal monologue, refined description image.
That's it. They fine-tuned the Qwen 2.5 VL model on this data. So now, given that math prompt, the LLM literally pauses and generates text like.
Like what?
I need to depict the steps of the equation. First step, 2x equals 14. Second step, xx equals 7. I will write these clearly on the board.
But here is where I got a little stuck for a second. If you start fine-tuning the LLM encoder, aren't you changing the embeddings, the language that the diffusion model relies on?
That is the classic modular AI fear.
Right. If you change the encoder, the image generator usually breaks because it doesn't understand the new signals. It's
Right.
like suddenly speaking French to someone who only speaks English.
But the authors anticipated this. They ran PSNE visualizations, which basically mapped the shape of the data to compare the embeddings before and after this fine-tuning.
And the distributions overlapped almost
He
perfectly.
did. The structure of the embedding space was preserved.
So the diffusion transformer, the part that makes the pixels, didn't get confused.
It was just receiving much richer, more logic-dense instructions within the language it already understood.
Okay, so SFT wakes up the reasoning capabilities. But the paper argues that SFT alone isn't enough.
No, it gets you part of the way there.
But to beat GPT-4o, they needed a second phase. And this is the technical core of the paper. Dual-GRPO.
This is where it gets really interesting. SFT teaches the model how to reason. But just because an LLM writes a logical sentence?
Doesn't mean it's a sentence the image generator can visualize well.
Exactly. It's the difference between being correct and being effective. The LLM might write a perfect technical description of a violin, but maybe the diffusion model responds better to a poetic description or specific descriptor tags.
So you have to align the thought process with the visual capability.
You do. GRPO stands for Group Relative Policy Optimization. The dual part is the key innovation here.
Meaning they're optimizing both parts at once.
Both. The LLM encoder and the diffusion transformer simultaneously.
They're training them as a team. That sounds computationally heavy, though. How does that setup actually work?
It's a reward-based system. For every prompt, the LLM generates a group of different reasoning paths. That's the group in GRPO.
Okay.
Then, for each of those paths, the diffusion model generates a few images.
So you have this branching tree of possibilities. One prompt branches into multiple thoughts, which then branch into multiple images. And then comes the judge.
The reward function. And they use different rewards for each part. The LLM gets a pat on the back if the final images have high semantic consistency.
So did your rewrite lead to the right result?
Basically. And the diffusion model gets graded on semantic consistency, aesthetic quality, and physical consistency.
Make it match the text, make it pretty, and don't break the laws of physics.
Precisely. Now, using GRPO here is smart because it removes the need for a critic model.
Which you'd normally need in PPO.
Right. In proximal policy optimization, you need a separate value model to estimate how good a state is. That effectively doubles your memory requirements.
So GRPO skips the critic.
It just compares the outputs against the group average. If output A is better than the average of B, C, and D, it gets reinforced.
That makes sense for the LLM side. But applying reinforcement learning to diffusion models is notoriously tricky.
Very tricky.
Because diffusion models, especially those using flow matching like most modern architectures, they're essentially solving an ordinary differential equation, an ODE.
Right. And ODEs are deterministic.
If you run the same prompt with the same seed, you get the same image. It's a smooth, predictable track.
And RL needs randomness. It needs stochasticity.
It has to explore.
It needs to try slightly different things to see what works better.
Yeah.
If the train is locked on the track, it can't explore better routes. It can't learn, oh, if I go slightly left here, the image is better.
So they used a technique called flow GRPO. How did they get around this?
They mathematically converted that deterministic ODE into a stochastic differential equation, or SDE.
Okay, let's not do a heavy math lecture here.
No. Think of it like this. The ODE is a train on a straight track. The SDE adds a little bit of wiggle or noise at every step of the journey.
Oh.
Specifically, they use the Euler-Mariana scheme during training to inject this noise.
So it's still heading to the destination, but it can drift slightly left or right.
Exactly. That drift allows the model to explore the space around the optimal path. If a slightly noisier path leads to a higher reward image, the model learns to steer that way.
That is incredibly clever. It injects just enough chaos to allow for learning, but it preserves the structure of the diffusion process.
And crucially, this allows them to perform that balanced training we mentioned. The text encoder learns to write prompts that lead to high rewards.
And the image decoder learns to render those prompts more effectively. They evolve together.
Yes.
So let's talk about what this actually looks like in practice. We mentioned the benchmarks, that 0.79 on WISE is a generational leap.
Yeah.
But the qualitative examples in the paper really sell it for me, specifically the Chinese idiom story, marking the boat to find the sword.
This is a classic test of logic. A man drops his sword into the river, so he carves a mark on the side of his moving boat to remember where it fell.
Which is logically hilarious because the boat is moving away from the sword. The mark is useless.
Totally useless. But visually, to tell that story, you need a sequence. You need the sword falling, the man carving the boat, and then the boat moving away.
Standard models must just hate this prompt.
They panic. They draw a sword floating in the air, or just a guy holding a knife, or an X floating on the water's surface. They just don't get the sequence.
And this model.
The Think Then Generate model nailed it. It reasoned. First, sword falls. Second, mark the wood. Third, boat moves.
And the generated image showed that logical flow.
It did, usually in a multi-panel layout or a composition that implied movement.
Another great one was Einstein's favorite instrument.
Sounds simple, right? But ask a standard model, and it relies on training data that might just produce a generic musical instrument or some mashup of a guitar and a cello.
Because Einstein and instrument appear together in weird contexts in the dataset.
It's relying on co-occurrence, not facts.
Right.
This model first retrieved the knowledge. Einstein played the violin. Then it reasoned. Violins are made of wood, have a specific shape, a chin rest.
And the result was a highly specific, accurate wooden violin.
It's the difference between guessing and knowing. And they didn't just stop at generating images from scratch.
They applied this to image editing, too.
With a model called Qwen Image Edit. This is where the reasoning becomes like a workflow tool. The test case was that melting ice cream one.
The instruction was simple. Draw what it will look like after being exposed to the sun for 1 hour.
And a vanilla model just hears sun and brightens the image. It changes the lighting. It treats sun as a style transfer instruction.
It totally ignores the causality.
It does. The Think Then Generate model reasoned. Sun plus ice cream plus time equals puddle. The resulting image showed the ice cream losing its structural integrity, dripping down the cone. It simulated the physics.
And the benchmarks backed this up too, right?
They did. On the Uniredit benchmark, they scored 68.7, which beat Gemini 2.5 Flash. It proves that the bottleneck in image editing isn't the pixel generation quality anymore.
It's the instruction understanding.
Exactly. We also saw some really important data in the ablation studies. They compared using just SFT versus adding the Dual-GRPO.
SFT alone got the WISE score up to 0.74. That's already a huge improvement over the baseline 0.61.
It is. But adding the GRPO is what pushed it to 0.79.
So SFT does the heavy lifting of learning the pattern of thinking.
But GRPO is what aligns the content of that thought with what the diffusion model can actually render.
They also tested staged training the LLM first, then the diffusion model versus balanced training, where they do both at once.
And balance one. It goes back to that idea of the two components learning a shared language. If you freeze one, you limit the adaptation.
Like a couple finishing each other's sentences, they need to be in the same room to learn that rhythm.
That's a great analogy. If you train the LLM in isolation, it might learn to write prompts that are logically perfect, but visually ambiguous to the DIT.
So bringing this all together, this paper essentially proves that we have been just underutilizing the LLM part of our diffusion models.
Completely. We've been treating them like static dictionaries when they could be active reasoning engines.
That's the takeaway. By unfreezing the encoder and applying reinforcement learning, they've turned image generation from a pattern matching task into a reasoning task.
It's no longer input text, look up features, output pixels.
It's input text reason about physics, plan the image output pixels.
It feels like a necessary step. We've all seen those AI images where the lighting is perfect, but the person has 3 arms or a reflection shows a wrong angle.
That's a lack of reasoning.
Precisely. We've conquered the texture. Now we are finally fighting for the logic. And what's fascinating is that this didn't require a bigger model.
Right. They used Qwen 2.5 VL and a standard DIT backbone. They just trained them smarter. This brings me to a thought for you to chew on. This paper focused entirely on text-to-image, but we are currently seeing an explosion in AI video generation Sora Gen 3 VO. And the biggest complaint there is dream physics. Objects morphing, vanishing, or moving in ways that defy gravity.
Consistency over time is the hardest problem in video. You see a car turn a corner and suddenly it's a different make and model. Or a glass falls and turns into liquid before it hits the ground.
So if Think Then Generate solves the logic of a melting ice cream in a static image, what happens when we apply this to video?
Oh, wow.
If a model has to reason about physics and causality over time using chain of thought before it generates a single frame, could this be the solution to the glitchy physics problem in AI video?
That is the billion-dollar question. If you can bake a physics simulation into the chain of thought, the ball hits the wall, compresses, and bounces back at angle theta before generating pixels.
You might finally get video that makes sense.
Not just visually, but physically. You're moving towards a world model.
A fascinating possibility. That's it for this deep dive into Think Then Generate. We'll catch you on the next one.
Keep learning.